So I'm going to start now. To make sure everyone is on the same page, it's really just poor man's metaclasses, not rich companies' metaclasses. So the idea of metaclasses was pitched by Herb Sutter recently, and they and he basically proposed something to allow us to generate classes at compile time with a more imperative syntax and based on reflection. So I'll start with a small example. One thing that he showed in his slides was a way to generate Qt properties. So Qt uses a special tool to create runtime type information. They use it for signals and slots to connect different Qt classes, and it's basically a second stage of your compilation. So you have to write a class, and it has to contain a macro that tells mock this has to be parsed, this has to be exposed in the mock type system, or in the type system of Qt with mock. And you have special macros that will then be replaced with code, and mock basically parses them and generates runtime type information inside several arrays that would be accessible for every class. The bad problem about that is you have to write a class. You can't put it into a template. So you can't make generic components of widgets, for example, that you can reuse, and you could use template policies to add elements into it. So with metaclasses, we probably could write something like that we just declare our normal class, and then in the current proposal, or in the current working paper, well, it's not a working paper yet, but the current base of discussion has the idea that you would add a const expr function to your keyword, like class or struct. That would be called with whatever you pass or what you add after it. So you can then operate on that and then generate code. So I tried this a little bit with the compiler on Godbolt. I think Andrew Sutton wrote an implementation based on Clang, and this is not complete, and it also doesn't generate the right information. But basically, what you have to do is you have to assemble an array of properties, and you have to assemble function pointers, and yeah, the details are gory, and I didn't complete it. I just wanted to see if it is feasible in some way. So this is our meta class. It receives a type. That's not the Q thing that you saw earlier. Instead, it's a reflection object, reflection type. And if you look at it, if you try to create a compile error out of it, you just see meta something and a big number, which is probably a pointer inside the compiler. So since it's not a real type, you have to use specific APIs to get to the contents. So you can, for example, call a member function called member variables, and then you can traverse all of the member variables. And this is not a real for loop, it's a special for loop where each block basically sees a different type, or sees the type of the element. So it's like a tuple for. And then there are special tokens, __ generate, which emits code fragments. And so you can, for example, if you have an existing meta type, you can directly generate it. And it would be written into the type that you modify. And you can also create new code fragments with a different token, and that one. So because you have processing outside, you need additional functions to get data from the processing that you did outside of this code fragment into the code fragment. So here, for example, you can take the type And yeah, well, what I tried to do was I wanted to look for member variables that are named property underscore, gather them, and then maybe look for member functions that have a similar name. So really doing it in a dirty string-based way. Yeah, but it didn't get very far, and that's not what we're going to do today. So this is just an overview of what I just said. 2 years ago, I joined Siemens, and we there's a framework I was working on, and it's called Cactus, and it basically is a framework to configure microcontrollers. So you have a microcontroller, and you want to read data from peripherals. You want to process them. You want to send data of those peripherals to your servers. And so to configure what this microcontroller does, we use Node-RED or XOT. So we assemble function blocks, connect function blocks with edges, and then we have an environment in which we can also trace what's going on the microcontroller. So this leads us to having node types that have parameters that come from our servers to configure them. Also values that come back to the server for debugging purposes or any type of processing that you would do on your server. And you have specific input slots and output slots that you want to connect. So we came up with something that's based on Deckel type. So this is an example application that is supposed to scale a value and is configured from the outside and also prints some debug information to the server. So we basically use Deckel type, and within that scope we are producing a value, but we only care about the type that comes out of it. So we then call a function called app, which tells us, okay, there's an app definition coming. We use app as term for those nodes. And then there's a compile time string telling us the name. So that compile time string can be used to create hash values, or we can just use the name. Then we declare each property, also with compile time strings to identify them. We give them a type, and we do that for all properties. And then we have to provide a function that operates, that does the purpose of this app. So because those are all compile time strings, they turn into a distinct type. And it's only, so this type is only defined by the value of each individual character. So each of them are distinct, and if I write them again, it will produce the same type. So I can use them as a lookup key in a container. And I can also implement name parameters with that. So yeah, this framework is currently closed source, and it's very entangled with different libraries that are where it's connected to. I mean, we also use it, for example, to directly connect it to external peripherals. So if you have a UART line and there's a communication going on with a different system, and because we have those keys, we can also declare this protocol based on those keys. So we can directly map data out of a protocol into the system. So we can, without any overhead, forward data through this and have a lot of code generated for us. So I have to say something about the compile time strings. They are not part of GCC, not part of the current standard. They are voted into C++20 and are also not part of the current draft yet, as far as I have seen. But the basic syntax is you write an operator, you define a specific prefix, suffix, and you get all of the characters as a variadic value. As variadic values. And yeah, you can do all kinds of things with that, because you can have different suffixes. You can also do, for example, a domain-specific language to represent a state machine. You can have states and events, and you can have user-defined names for that, and you can be sure that that they will never collide. You will never have cases where someone accidentally puts the name of an event where it should be a state or whatever. And there are already libraries that do that. So you can also go back to a character string out of this compile time string by simply storing it inside an array and never forget the null termination and then return the whole thing. So yeah, those things are not null terminated yet. So yeah, you save one byte. I already said it's not part of the draft. It's not part of the draft, but voted in. And it's available in Clang since, I don't know, I guess Clang version 3 or 4 and GCC 4.9 or 5.0, I don't know. But it's at least for all of the compilers I usually work with, it's just available. And in GCC 9, they made an implementation of that proposal, which means they disable the warning that comes up when you try to use them. And they also implemented the other parts of the proposal that make the allow more generalized values inside template parameters. Because right now we can only use characters, pointers to external symbols, and integers as template parameters. So now we can even use structs as template parameters. But it doesn't really change the downsides. So if you have an API and you use them inside your API, since it's part of the API, you would generate a symbol in your API that contains the whole string. So you end up with a very long API name, and that's probably nothing that you want to have. There might be binary format limits that you don't want to exceed, so it's something for internal processing. So we have those compile time strings. So now we're going to do generative programming without reflection and without metaclasses, just by defining a compile time front end and doing processing on that, on that definition using quasi Empl. So I couldn't use Cactus as an example, so I thought I would do something else. I recently had to deal with Amazon Web Services, and they have a very broad API based on REST requests, and they have a specification, and they have a horrible SDK for that. So basically, all of those services that they provide, they have a distinct JSON payload that describes them, and you so for each request you have a different JSON payload, and you have different responses that you might get, and all of that is in a big JSON file describing what's going on. So they made a code generator that would turn every request and response into a class, and that class basically just does boilerplate serialization, and it has an inheritance hierarchy, so you also have virtual function pointers, and you also don't you can't really optimize it away, because there are some central classes inside each of those libraries that reference each of those request and response types. So as soon as you use one of them, you basically pull everything in. And if you work in an embedded environment, or even want something like a WebAssembly application in C++, you don't want to use that. So we're going to write a front end for that. So we have requests and responses, and we just each of them has a distinct name. So we add a name parameter. We have probably some configuration values. We don't care yet. All we need to do is declare a function and declare a return type. We don't care about the body, just have names, just have function names that tell us something about what's going on. We of course have to define some types, but also the contents don't matter much. And then each of the requests and responses are grouped in services. So yeah, let's add a service definition that has a name and some of the host prefix information that you need to know to which host you want to connect to. And that adds another parameter to our request and response functions. And we do that with every part of this definition. We also declare the JSON payload. That's the most important part because that identifies the replies. So, it also contains the parameters, but so we'll have a basic function that tells us the following definition will be the JSON payload, and then we have the ability to declare parameters that have to be provided at runtime. That might be different based on your request. And we need some fixed name value pairs. And of course, we need something for structural elements because you can have objects inside JSON that have other objects and on. So we do that for everything. And then we can declare, for example, the Cognito secret remote password API. Just by using something like this. So we declare the service, it has a name and it has a host prefix. The request is named, it references Cognito. Though the basic interaction to get authenticated is initiate auth, and we have to provide which part of the interaction flow we want to see. And then we have a JSON object that has two parameters that we have to provide. Details don't matter much, but yeah. Then there are possible responses, like we can get an error like user not confirmed or user not found. So we add also functions for that. And maybe something else that is obviously not documented properly. And we also reference something similar that we just saw before, which contains also like 4 different values. I'm not going to show it on the slide, it doesn't really matter, but we also reference what we expect to get back. So when we do our communication, we will at some point parse the result and see if everything is inside, and then realize, oh, okay, this is the response I wanted to have. So I missed something. So far we only have to define functions, and all of those functions had variadic parameters, so there was no restriction at all. I could combine them in any way and it wouldn't make much sense what comes out of it. If I work alone on this project, or if I want to work alone on this project, I would do nothing and create no compile errors and don't save people from abuse. But it would be better to catch the error early. So we will add either static asserts in the proper places or standard enable FT, which in this case would disable specific functions to be called. So we have to provide a Boolean expression, compile time expression that tells us if this function call would be right. And if it is right, we would just add the type that we expect. So since we have variadic parameters, we need some help to make the check easier. And here comes classier Empl to help. So when you want to check that criteria is satisfied for all parameters, you could use classier Empl all, which executes a predicate on every parameter that you pass in and tells you if all of them satisfy that criteria. So you have to provide a template meta function as a predicate, and you have to provide a continuation. More on that later. So basically, those the predicate. Sorry. So the predicate is required to have an f as a member type. This could be a type alias or a struct. It doesn't. It depends on what you need. So in our case, the easiest way is to have a struct that is a Boolean, and we can make compile time checks. So for payload, to see if a payload is valid, we would require that you have to pass in an object or a parameter, or ensure, but doesn't fit on the slide. And so with that, we can basically restrict our payload definition, and we do that for all of those functions that we have. But I haven't explained yet how to then pass in the parameters. And classier Empl uses a specific style of metaprogramming where you assemble an algorithm by putting algorithms together. Each of the algorithms has a continuation parameter where you can basically put the following algorithm into it. We'll see more examples of that later. But for now, that's enough to understand the next slide. So we would then define payload like that. We do MPL call, MPL all, valid payload, pass in all of the t's that we get as a function parameter, and then return if it's valid. Return t payload as expected if it's valid. So as an overview of what we just did, we have a domain. We look for specific speaking names and turn them into functions without a body. And we can, if we want scopes, for example, if we want to assemble stuff that is more complex, we stick into each other. And we can use global constants for things that are singular and unparameterized. We are using compile time strings because we need serialization features. We could also use text structs. And we use carefully placed enable ifs or static asserts to make sure that errors happen at the place where the people make the errors. So the next step is cogeneration. So we now have a big type that we want to somehow transform and generate runtime code out of that. In our case, we want to be able to write a function like this. We want to use ASIO, of course, and we want to specify the request that we want to execute. We only want to specify the information that is relevant for the request. And we then can also still use our compile time string to identify the specific parameter. So in the case of initiate auth, we pass in SRPA and the username. And we pass error handlers and successful result handlers. And as you can see at the equal sign, at the assignment, that something is going on here. So this one is also a variatic function, and because we don't know exactly how many parameters we need for our request, and you could have like a lot of different error handlers and all of that. So we are going to write a name parameters library now, or utility now, to be able to pass in name parameters to our functions. So with that, we just have to add an assignment operator to our compile time string class, forward the value that we get, and store it in a specific type that will only hold the actual value. And it would look like this. So there's a, yeah. So this is the key type, and this is the value type. We only store the value type. There's an optimization possible where you derive from the value type if it's an empty type. If you want to look at that, you could have a look at Boost Hannah. It does that. It's also not complex, but yeah, just to mention it. So then with all those items that are created through assignments, we put everything into one big storage type that derives from each of those items. This makes it simple to later access the individual value. So this thing doesn't need more than 2 constructors, one for copy and one for initializing each individual value. And there again, we would use MPL. That's a detail I won't show. So we also need to make sure that no one uses params in an illegal way or uses our function in an illegal way by not using an assignment. So we just use a static assert here, MPL call, MPL all, and check if each of the individual parameters is an assignment. So now comes the code to access an individual value. So you basically we just since our parameter storage derives from each of the individual assignments, we just have to cast to the right one and access the data. So for that, we just need to know the value that we want to expect, but we don't know it because we only provide the key. So we again need classier magic to get to the value. And there comes in another classier algorithm handy called findif. It takes your variadic sequence and goes to the first one that satisfies a predicate, and then returns this as the result of that algorithm. So, for example, if we would invoke it with this sequence of items, and we are looking for the one that has standard string as key, we would basically get this list back. So we need to get rid of this one. And there's another algorithm that helps here. It's called front. It basically just takes the first element and it omits the rest. So with that, this is all we need to implement a named parameters library. And so we here just call MPL, search for the key, and omit the rest. The result of this whole expression is the value type, which is item key value in this case. We cast to it and we are done. So now let's take the further steps. We now have all of our parameters in a way that we can easily process them and work with them. We now need to disassemble our request definition. So we need to get the request, figure out how it should look like, and create a JSON payload out of that. So for that, we're going to use the format library and also MPL to get to the data. So our request type is one single type, and quasi MPL works on variadic types. So for classier, it would be just one element, so we need to unpack it. So we will use unpack to remove this part, and we'll use findif to find the actual payload part inside this sequence of types. So we end up with a list containing the payload, and we can then use front to omit the rest. And then again, we can unpack to get to the contents of the payload. So we end up with this definition to basically reflect on our request type and only take out the payload definition. Now for the payload definition, I'm going to use a different technique. So like the horrible way of basically unpacking a type at compile time by calling out other functions. So we will basically use functions that unpack parts of the type by using the pattern matching of the compiler. So if we put t-payload into our parameter type declaration, we get access to the elements, and then we can use this fold expression to execute the following steps. So we end up disassembling the type by calling out functions individually for each part of the payload definition, and we will reach leaf parts where we would put in the runtime parameters that the user has passed in using our name parameters. So we can basically expand the tree at compile time and create tiny little functions that assemble the string that we want to send off. And yeah, that's basically sending off. But after that, we'll get a reply, and we'll need to detect errors. That's basically trivial, and so going to skip that. And we also have to match our parameters. So we have to match whether the reply matches with our definition of the reply payload. That's what I want to say. And so we basically have to do the same in an inverse way and see if everything is available. So we're going to parse the JSON, and yeah, instead of formatting, we'll just see if the string that we expect is inside our parameters. And yeah, if it is, we'll return true, otherwise we'll return false, and we can also parse out the contents of the JSON payload and stick it into our parameter storage. So those are different parameters now. Those are not this is not the name parameter storage that we saw earlier. It's not the stuff that the user provided, it's the stuff that we get back. And it is defined by the contents of the reply payload. So yeah, this is the point of the talk where the presenter realizes the stuff that he's showing is far too complex. And the whole premise of doing generative metaprogramming with Empl is just too complex. But yeah, at least we try to understand what's going on here. So again, we're going to unpack. So we are now at the response payload. So we're going to unpack the payload. We have to somehow flatten this tree of nested objects with fixed strings and variable strings into a flat structure and turn it into a name parameter storage. So we're going to flatten this. We are going to filter for only the parameters. We are using another algorithm here to transform anything that's a runtime parameter into a item that we can use in our name parameter storage. And then we'll pass everything to the name parameter storage that we had earlier. So flattened object is something not provided by quasi-Empl, so we have to implement it our own. So what we need is to recursively traverse this type tree and look for objects or t-object declarations and extract the parameters of it and provide it as a result to the caller, and do that for every step, and then we end up with a big assembled list of parameters and fixed parts. I think it's not reasonable to go through it one by one, but we'll do it anyhow. So this one here is our entry point. We receive all of the parameters here. We want to join all of the results. Join is an algorithm that takes multiple lists and provides one big list out of it. So just what we want to. And then we have to recurse into the type tree. So we we will transform all of our parameters before putting it into join. So there we have a structure called flattened Empl. It'll be specialized for the normal case. We just return a list. And for our objects, it'll do the same as above. So again, we take out all of the parameters, we flatten them, and join them. And as a result, put them back to the caller. So step by step, we basically have our payload definition, which is a sequence of ensure, object, params, and whatever. We unpack it so that we only have the sequence of elements. And then we have to flatten this. So we have to remove any node that is an object and only extract the parts inside. And then we have it in a flat structure. Now we don't care about anything that's fixed because we only want to forward runtime information that we received from the server. So we filter out anything that's fixed, and we have our two parameters. Then we turn them into items. We use the compile time string as a key and the value type as value type for the item. And then we use this little helper to squeeze everything in params. So there we have our named parameter storage again. And with that, we can do anything we want. We can also use that as a normal tuple. We could invoke functions with it, and so on. So like the handler function that we had in our API. So what I tried to show today was a way of doing reflection now, which isn't really reflection, but just because we can't do reflection doesn't mean that we shouldn't work in that direction. So instead of reflecting on an existing type, we create our own information, the information that we want to work on. We do this by having a lean, completely type-based format, type-based front-end, and then we transform it with the help of metaprogramming. So we saw a few common, frequently used techniques and algorithms from classier, and we did some cogeneration stuff. So I think techniques like that are helpful if you have a very specific task. If you have a very restricted area that you work on where it's easy to find a domain-specific language or domain-specific way of representing what you want to see, and you can then tailor that for that specific problem. So it would make, I guess it would make sense to have a generic REST DSL, and because like AWS in this case, it requires a lot of specific functionality, like the reply matching, error handling. But because it's very limited, the actual implementation isn't much more cool than what you have seen here. There's just a little bit more repetition and a few additional small helpers. And because of libraries like classier MPL and because of variadic templates, it's really fast to operate that. I started doing metaprogramming in the times where we didn't have that, in the times of modern C++ design, where everything was a recursion, everything was just two types that you operate on, and it's in no way similar to that. In the cactus framework I showed you on the first few slides, the actual templates don't hurt. They don't hurt our compile times. They hurt linking times, yes. And we need a lot of memory for linking. But besides that, the price that we pay is definitely worth what we get back. So one thing I would like to add is that you should invest time for your for the functions that you use to define your front end, because that's the part that most of the people will use. and you don't want to come into the office and be in the middle of a big intervention that you should stop doing this and whatever. So you should look for a clear intent. It should be readable. It should be obvious what's going on. The code underneath can be horrible, but at least on the front end level, it should be easy to use, and it should have clear errors. So handle errors early and not too late. So the stuff I showed is on GitHub. This is a link to classier Empl. It's still being maintained, but there's not much feature development. It's kind of is complete. And I also encourage you to look into the implementation. There are a lot of interesting ways of doing things inside and stuff to learn from. So yeah, we still have a lot of time for questions. And I have some horrible bonus slides that I don't want to show, but if you want to, you can see them later. I'll also upload all of the slides. So I basically try to do the whole generation of the formatting of our payload in a single formatlib invocation, which means you need to assemble compile time strings and find a way to put commas between JSON objects and all of that. But yeah, if you have questions, shoot. You want to see how bad the slides are? Okay, let's go. Yeah, we don't want to do the recursive unrolling, where we go through the tree of types and call a function for each individual one. We want to have a single formatlib call. So I've replaced it to make it a bit shorter and to not have backslash or weird formatting because of the binary literals. Just single quotation marks as an example. We have a tree structure of types, and we want to unroll in a way that we have this string in one place, so that we can call format library and pass in all of the variable parts. And yeah, we need to do double closing and opening braces because format library uses those for placement of parameters. So we are going to use a small utility that assembles, concatenates strings, compile time strings. It's also already in the library. And we're going to use another little utility that takes an individual item and turns it into a substring of our format. So I'm going to use this little shortcut to make the slide smaller. Those are the quotation marks inside JSON, and this transform parameter would take the type, and for a parameter we use this placeholder for format library, put the name of the key value pair together with the quotation mark and the other string, and assemble a string. And we do the same for the ensure parts, where we take quotation mark, the key name, and now instead of the formatlib parameter, we're going to use the other compile time string. And yeah, then we need a change to our flatten library, because we need to flatten algorithm, because we need to at each level also invoke another nested algorithm. So this is the change that we need to do. We need to pass in the nested algorithm and execute it at each recursive level of the flatten code that we had earlier. So instead of just joining the results directly, we take this algorithm and put the parts through it before we join. We first join and then put it through. Sorry. Yeah. So with that, we get to a place where, oh, that's badly formatted. Sorry. We get to a place where we can get the all of the individual strings, but we are losing the structure. So we are losing the object information that it's encapsulated in another JSON object. So these are now on the lowest level instead of structured. So we need to add parentheses to structure them. So in our nested algorithm, we just do push front with the open and push back with the close parentheses. So we now have at the places where we had our objects, we now have opening and closing parentheses. And we also need to add commas. And this is ugly because we only need to have commas between two elements. And so the trick we are going to use is we are going to add a sentinel type called listStart at the beginning of each object. So we can later identify it, oh, there's a new object, I don't need a comma. So we have the listStart, and then we use a fold algorithm to assemble one single string. And the fold algorithm, again, is something that needs a predicate. And this time, this is the next slide. It's a parameter interleave element. What it does is, or basically what fold does, it takes a sequence and adds the next type. And with the help of the predicate, you have to define the current state, the new current state. So you can, yeah, it's basically accumulate. So the interleave element predicate will take the left and right type and just add the comma in between and concatenate that into a single string. And if we detect our sentinel type, we don't need to add the comma. So we figure out this is the beginning of the list. We can just ignore the sentinel type and return the one string. So yeah, that's basically it. With that, we get a big compile time string containing the whole Madlib invocation. But yeah, you don't have to do that. I mean, you can still do the slightly simpler way of unrolling your type.
This is faster.
You only have one Madlib invocation. You have one single string. So in the binary, you will only have this one string for each request.
Madlib can really make use of that one string.
Yes. Yeah. Well, I think Madlib also has some compile time literal version now, where you also can make some of those parts faster. So, like you could forward that then as a compile time string to Madlib. Takes ages to compile? Okay. But I don't know.
It doesn't surprise me.
If you look back at the AWS library, AWS SDK, it took on an i7, it took 5 hours to compile, and it's non-templated C++ code generated. Yeah, and because the way they generated it, yeah. I mean, this here doesn't really impact your compilation, because you will only have a handful of requests that you will need in your application. You will auth to the API. You will have some more requests to handle different errors, and then have one specific service that you might be interested in. So you end up with a handful of calls. Yeah.
Right, thank you.